Okay, everyone, we're back to our final two lectures of the course. I will now introduce Wenbo Gu, who's bringing a talk about optimization of intensity-modulated proton therapy. Hello. I will just really quickly introduce you. So Wenbo Gu is currently a medical physics resident at the University of Pennsylvania. She grew up in China and received a bachelor in engineering physics at Tsinghua University. I hope I pronounced that properly. She has worked as a research assistant on medical imaging at Tsinghua University for 1 year, investigating the motion correction effect in PET MR imaging. She pursued her PhD in physics and biology and medicine at UCLA, where she focused actually on treatment planning and inverse optimization. So we're looking forward to your talk. Go ahead, the stage is yours.
Thank you, Barbara, and thank you for the nice introduction. I'm really happy to be here to present my work and also the optimization of proton therapies. Let me start sharing my screen. Is that the correct screen you can see?
Yes, perfectly.
Great. Okay, I think I can get started. Hey, everyone, I'm Wenbo. I'm currently a medical physics resident at UPenn. Today, the topic I'm going to present is about optimization problems in intensity-modulated proton therapy. Okay. Here's the disclosure of my work. I just want to give a simple outline what I'm going to talk about today. First, I'm going to give a simple introduction of IMPT treatment planning. I want to talk about how to formulate the planning and optimization problems from a research perspective, how to start to your own optimization questions. And then I'm going to introduce my own research work, mostly on proton beam orientation optimization, and also how to integrate robustness into BOO problems. Okay, now let's first look at the treatment planning process of proton therapy. When we get all contours ready and start to planning, the first step we will do is to select the proper beam angles for the specific patient. Here shows a view of a proton treatment room. We have gantry and a couch. So the beam is from the snout. Let me see if I can turn on my laser pointer. Okay, so the beam coming from the snout shooting to the patient lying on the couch, and both gantry and the couch can rotate in their own directions. So for the beam angle selection, we need to choose a proper or a few proper gantry and the couch angles that fit into that target both best. And the next step, after having the beam angle ready, we need to position the spots from each beam to cover the target. And this step is to determine both the energy and the lateral position of the pencil beams. We know that, assume we have a target here and the beam coming from this direction. We know that proton is delivered layer by layer, where one layer means the proton pencil beams have the same energy. Okay, have the same energy, and the proton delivery, it will finish one layer and move to the next layer. So the first thing we want to do is to determine the proton energy to cover from the distal point to the proximal end of the target volume. And if we look at each layer specifically, so each layer we can break it into a grid. Well, we can position the break or the spot of the pencil beam to regularly to cover this layer. So like here, I have a target here, and the blue spot is the position of the pencil beam. And here we formulate the spot position that can cover this slice of target. And every pencil beam, every spot has its own intensity, or the MU in treatment planning system. And so we can, and then we can formulate this vector, spot intensity vector, or I call it fluence map, borrowed from IMRT. Well, each element in the vector represents the intensity of every spot. So like the X1 is the intensity of the first spot, X2 is for the second, and so on. After we position these spots, what we can do next is we can calculate the spot, calculate the dose from these pencil beams. So assume in this beam, we have 6 spots, and this can formulate a fluence map with these 6 elements. And we have a patient volume, which is 3 by 3 by 3 voxels. That make us having 27 voxels in total. If we have, if we let the first spot to have 1 intensity, and then we know it's going to deliver some dose to the entire volume, while some voxels may get higher doses and some may not. So this will give us a volumetric distribution of dose in this volume. And then we can write it, we can just write the dose in each voxels this way. While, so A, like A sub 2(1) means the dose from the first spot to the second voxels in this volume. And then what we can do is we can stretch this volume dose to a vectorized dose. This gives us a column here, which represents the dose from spot 1 to every voxels in the patient. And the next, we can just repeat this work to add to every spot, do a dose calculation to every spot, and this will give us a matrix. This, I call this dose calculation matrix, denoted as the capital letter A, and each voxel or each element in this dose calculation matrix represents the dose contribution to each voxel from a single spot. Why I want to formulate this A matrix and why it's important is because with this A matrix, if we know the fluence map X, then multiply these two, we will get a vectorized, we will get a vector, and this vector is actually the actual dose delivered to the patient. So that's why we need this A matrix. However, in a treatment planning process, this fluence map X is actually the variable. So we don't know what's the real number of this, and that's also our goal to get it. But on the other side, we know what's our desired dose is. We know we want how much prescription dose to our target and lower dose to the critical structures. And also the dose calculation matrix A is also known from our previous preparation. That makes us able to do what's called inverse planning to solve some problems and get the fluence map X. And this step is, this inverse planning in photon therapy is called fluence map optimization. So I'm just going to borrow this concept and call this fluence map optimization FMO as well for this part. And the real meaning is to acquire the actual spot intensity map. Now let's look at how we can formulate an FMO problem generally. I'm showing an equation here, which is a very commonly used quadratic dose fidelity cost to optimize X. In this function, so we already mentioned A is the dose calculation matrix, and if I is a specific structure like PTVI, and so the A sub I here will mean the those calculation matrix block. So just getting the voxels from that structure. And therefore, A sub I times X times the fluence map will give us the vectorized dose delivered to the structure. P here is the prescription dose for this target volume, and then can see A sub I times X minus P is actually a deviation from the prescription dose of every voxels in the PDV. If that voxel just get the prescription dose and then the difference at that element is 0, and the larger the difference is, the larger the number is. And then we can use this quadratic term, the L2 square, to make this vectorize the difference into a one single metric. And the larger the number is, just more deviated the dose is from our expectation. And then we can use a structure weighting parameter to weigh this. The more important the structure is, and the higher weighting we can put on this. Okay. Next is the fidelity for the OERs. It has a similar concept, just instead of prescription dose, we use a maximum allowed dose here, MI for this OERI. That means if the OER in each voxel, in that voxel, is getting lower than M dose, then we are okay. But if it's not, then we want to penalize it. We can also set M to be 0. Then we are penalizing any like non-zero doses in the OER. Here we add a one-sided function here, one side with this positive sign. That so what this function do is, if for the vectors within this one-sided function, if the element has a value not negative value, then it will keep its number. If it's negative, it will make this element 0. So what this entire term can do is, it's just like it's just keeping this OER that has dose larger than the allowed number and penalize this. We still can use a quadratic term and a weighting parameter here. So the function goal is to get the deviation of the doses from our prescription and minimize the cost value, because we want the dose difference from our expectation to be 0. And the second rule here is a non-negativity constraint on X, because we cannot have negative spot intensity or negative MUs. This problem is for the quadratic term, it's like easy formulation, and it can be solved by methods like gradient descent. But I also want to mention is, it's just one of the many ways to formulate the problem. We can, in addition to quadratic function, we can use like dose volume constraints, or like mean and the maximum dose constraint as well. So here shows an example to, instead of just penalize each voxel using a quadratic, we can penalize the mean dose in the OERs and the maximum dose in the OERs. Just when starting a research project, quadratic term is usually this most simple and the most like easy to solve problems, because of it's smooth and it's differentiable. Now let's move out slightly towards my research project about beam orientation optimization. Okay, so let's look at, or go back to this clinical workflow to get a treatment plan. We noticed that beam angle selection in current clinical process is, okay, so let me say, so first, how many beams are usually used for proton therapy, for IMPT. The number is typically 2 to 4 proton beams used. This is because the unique proton beam physics, the limited beam time, because in many centers, the beam are shared, the beamline are shared across different treatment rooms. And we also want to reduce the body dose. That's why we also don't want to shoot too many beams. This small number of beams make every beam of IMPT plan will heavily affect the final plan quality. And in current clinical process, these beam angles are actually manually selected recently. So, there's many challenges in using the manual selection process. For example, it needs a lot of experience from the planner to know what's a good angle. And even from experienced planner, the optimality is still not guaranteed, because it's really hard to search in the entire non-coplanar space to find a good combination. While for proton, especially for sites like brain, it's very common to use non-coplanar beam angles. For some complicated cases, we also might need to do a few trial and error runs to keep testing, go back to run with these steps, get our fluence map back, get the dose, and see if the dose is acceptable. If not, we may need to go back to the first step to reselect another set of beam, and do this all over again. So this definitely means lower efficiency of planning. Let's look at a few factors that we need to consider if we want to do a beam angle selection. The first factor is, of course, dosimetry. We want good OAR sparing while covering the target well, and also we want low dose to normal tissues. Second factor is robustness. It's also a very critical factor in any part of proton planning, because IMPT is very sensitive to uncertainties. Like proton has this sharp drag peak, of course, it's the advantage of proton, but it also makes it very sensitive to any errors. A little shift of the proton drag peak will make the dose very different. And also for multi-field optimized IMPT, in a single field, the dose in that field is very heterogeneous. That also introduce more uncertainties of the plan. There are some sources of errors, uncertainties. For example, setup errors, which is also common to photon therapy, that the patient position can be different from the planning CT. And also range uncertainties. This one's more special to particle therapy. It means that the proton range will be, the actual range will be different from what we expected or what we see on the treatment plans. Factors like CT artifacts, uncertainties in CT number, and the conversion from a CT number to stopping power, like those calculations, will introduce these range uncertainties. And of course, motion, interplay, anatomy change will affect the plan quality. Another factor I want to mention is biological effectiveness. And this, so the biological effect of proton is characterized by this RBE number, while in clinical use, it's usually have an RBE of 1.1. That means proton is about 10% more effective, biologically effective compared with photon. However, it's not really accurate for real proton beams. Like here, the figure here, it shows that RBE can be quite like constant in the entrance of the proton beam, but when reaching the end of proton range, RBE actually start to increase and get a number between probably 1.5 to 2. And what's the effect and why it's a concern? It's because if there's a OAR sitting just right here in the distal end of this beam, so from physical dose side, we may see a very nice low physical dose, but that may not be true. That may be actually higher biological damage to the critical structures. So that's one thing we want to avoid. And in clinic practice, it's always recommended to avoid pointing the distal valve directly to a nearby OAR. Okay, so now let's revisit this workflow. We said it's low efficiency, not very optimal. And how can we possibly improve it? Let's see. So the first step is a manual beam selection. The middle two is actually can be handled by the treatment planning engine to do an automated computation. And then the inverse planning part is automated optimization, but requires some manual tuning. So can we do this in another way? Like for example, since these middle two are automated, can we just do these two first, and then we can integrate beam orientation and the fluence map optimization together, make this first and the last step just in one step, which will be an automated step, might need some manual tuning, but still like less steps. And from this step, if we can get both the beam arrangement and the final dose distribution, that will be more optimal. So that's the motivation of our research works. We want to integrate these two into one and then make it more automated. So let's talk about automated beam orientation optimization. We mentioned that we want it to be less human dependent. We want it can do a global search in the entire 3D space to find us the optimal solution. And also we want to integrate BO and FMO for better planning efficiency. And just mention these factors to consider: computational efficiency, dosimetry, robustness, and the biological effect. Let's focus on the computational efficiency first for right now. Oh, sorry, the computational efficiency and the dosimetry first for now. See if we can have this framework and the targeting on these two factors. Therefore, next I will talk about a group sparsity regularization based BOO to use group sparsity, integrate BOO and FMO, generate beam angle and a fluence map in a single step. Okay. Let's see how we can formulate this problem. Assume B as the set include all candidate beams, and see if we assume these candidate beams are spaced 6 degrees equally in the entire 3D space, then we will get about 1,100 candidate beams in total. And our goal is to select 2 to 4 out of this 1,100. There might be some candidate beams are not feasible, like have collision issue and also like passing through patient body that's not very desired. And then we can exclude these non-feasible beams in this step. After decide our candidate beam set, we can then position the spots in each candidate beam to cover the target in each direction. So this will give us the fluence map X over all candidate beams. And if we look at the formation of the fluence map X, we can see it actually consists of every candidate beams, and so it will be a long vector And this is our optimization variable. With the spot position, now we can do a dose calculation for each candidate beam and get the dose calculation matrix A. And still, we want A to include the contribution from all candidate beams. And we formulate A in this way. So concatenate the beam contribution in the column direction. Now let's take a look at our objective function to do BOO. The first two terms we already learned. It's the dose fidelity term on PTV and OERs. And one thing to pay attention is, so this dose fidelity includes the dose contribution from all candidate beams, because both A and X, including all. The third term is the core of the objective function. It's a group sparsity regularization for selecting beams. We can see why it's called group sparsity, because it uses an L2P norm to group the spot intensity of each beam. So X sub B is part of the X that is the spots belong to this candidate beam. I want to give a simple example why group sparsity regularization can be used to select beams. It's so we can break down for X, it's the combination or concatenation of all candidate beams, and all candidate beams. So also for every candidate beams, it consists of multiple or a lot of spots, and every spot in that beam can have some intensities. So that's how a X vector looks like, for example. And with the group sparsity regularization, what it can do is it will try to make, in some beams, like the second beam, to make every element to be 0. And when every element is 0 in that beam, we can call this beam as inactive. So this beam is not selected. So by doing this, we can make more and more sub-beams to have 0 intensity and therefore being inactive. Here shows why the group sparsity can make it 0, make some beam to be identically 0. If we have if we assume P is equal to 1/2, and this is how we can calculate the L2 1/2 norm, combining the spots of every candidate beams, because we are trying to minimize the term. The entire function is to minimize the cost. And if we want to minimize, and every beam is already grouped together, so a good situation for minimal value is to have some numbers to be 0. So let's assume, so this term is going to be 0 because we want to minimize. And the only condition can make it 0 is that each element within it is 0. That's why this beam become inactive. So if we can choose a proper weighting parameter alpha here to the group sparsity, we are able to force most of the candidate beam to have identical 0 intensity. And this leaves us to only 2 to 4 beam active. And this number, the number of active beams will depend on the weighting of alpha. And in the meantime, because we see like here, while some beams are completely inactive, some still have non-zero intensities. And these non-zero intensities is used to satisfy the dose fidelity, to make the dose more, to lower the dose cost. So that's why we can have the fluence map X simultaneously generated. And for the group sparsity, there's a few options how we can choose the L2 norm. Like we can choose P equal to 1. This will give us an L2 1 norm, which is convex. But we do find that some potential degeneracy issue within this L2 1 norm, which I will show some results later. So we also tried L2 1/2 norm, but this will make the problem non-convex. The last term is just a non-negativity constraint on X because we cannot have negative spot intensity. Therefore, we formulate this group sparsity based BOO problem, which is used to optimize for optimal dosimetry and acquire beam composition and the intensity X in the same time. Remember that A and X includes all the candidate beams. So that means this problem is a very large scale problem. And also because of the L2P norm, the group sparsity is not smooth. The algorithm we choose to solve this problem is called FISTA, short for fast iterative shrinkage thresholding algorithm. The advantage of FISTA is it can use to solve that non-smooth objective function, and it also have an optimal convergence rate among first order optimization method. How to solve this problem in using FISTA, I'm not going to detailedly describe it, but you are able to find this in this medical physics paper in 2018. We tested this algorithm on 4 patients, including 3 unilateral head neck patients and 1 base of skull chordoma patient. The dose calculation is performed by Merit in MATLAB. And here I want to, because I know we just have a lecture on MATLAB as well. I want to say big thank you to all authors for Merit. It really helped me a lot to start and build up this optimization framework. So let's go back. Since we want to calculate all candidate beams, the dose calculation takes a slightly long time. Depending on the target size, it can take half an hour to an hour for 1 patient, but that will be the preparation time, doesn't need any human intervention. And then the group sparsity BOO optimization time itself takes about 2 to 10 minutes for those 4 tested patients. And we compare our method against the plans with manually select beams. Let's take a look at the beam angles. So this is the candidate beams, and the second to the left is the manually select beam for this chordoma patient. And here shows using L2 1/2 norm group sparsity or L2 1 norm group sparsity. In order to keep the result comparison fair, we decide to adjust our tuning parameters. So our BOO algorithm have the same number of select beams as the manual plan, which is for 4 for this case and 3 for the head neck case. Since our goal here is to get a good dosimetry, so let's look at the DVH comparison of the BOO plans versus the manually selected beams. So the solid line is the manual plan. The dotted line is the L2 1/2 group sparsity, and the dashed line is L2 group sparsity. For this 4 tested case, we can see like all the 3 methods have similar PTV coverage, while for OERs, compare the dot line with the solid line. So our L2 1/2 norm is able to, sorry, not required. sorry for interrupting. So we can see a lower OER dose using our L2 1/2 norm. Like I label some structures here. For example, the left parotid, the right optical nerve, the carotid, and the left cochlear for these different cases. And if we compare with our L2 1 norm group sparsity, we do find some issue because of the norm term that the OER sparing is not well guaranteed. So for example, the left parotid dose and the left cochlear dose is reduced from the manually selected beams, but the chiasm dose and the carotid dose is getting like higher on the other side. And so our conclusion is that we formulate an integrated non-coplanar beam orientation and the fluence map optimization framework. And we found L2 1/2 norm group sparsity is more effective for beam orientation optimization. This framework can give us a very computationally efficient solution, like less than 10 minutes for these tested cases, and result in dosimetrically competitive plans. And this step is less human dependent. And also the flexibility within this group sparsity framework allows us to formulate more problems or solving more problems. For example, let's talk about the next project about robust BOO. We mentioned the first work, the goal is to optimize for good dosimetry. And next, we want to consider robustness into it because we just know IMPT is so sensitive. If robust is not considered, then the plan is just not very reliable or trustable for clinical use. Let's see how different beam arrangement can affect the plan quality. So here shows for a base of skull patient, the target is at the skull base, and we have 2 beam arrangement. The first one is 2 lateral beam and 1 vertex beam, and the second arrangement is an anterior posterior combination. And here shows the DVH of beam group 1 and the beam group 2. The solid line here, or also this is a DVH including nominal dose that's no uncertainties, and also some worst case doses, like if the patient is misaligned by 3 millimeters in each direction, or the range is overestimate or underestimate by 3.5%. So this kind of plot shows both the nominal DVH and how sensitive the plan is. The wider different lines spans, then the less robust the plan is. So we see for these 2 beam groups, the CTV, so group 2 has less CTV robustness. So under different cases, the CTV dose will change more compared with group 1. But on the other side, the dosimetry, so the dose of the brainstem from group 1 becomes much higher in compared with group 2. So this proposed question is, since beam angles will affect both dosimetry and robustness, can we develop an automated beam orientation optimization algorithm that consider both and optimize both? So that's our goal. And let's talk briefly about the conventional robust optimization. The conventionally used method is called worst-case scenario optimization. In this method, it will calculate the worst cases, the largest setup error or the largest range uncertainty that can happen, and then penalize those deviation under the worst cases to ensure acceptable dose when some kind of uncertainty occurs, and this uncertainty won't be as bad as worst case. But there's definitely a few limitations within this worst case method. First, the normal tissue sparing might be sacrificed for robustness because we are considering worst case. But worst case might not really happen in real situation. So the plan might be over conservative. And then dosimetry is OR sparing might be sacrificed for this over conserved robustness. The second issue is because for robust optimization, we need to calculate all these different cases. That means both the computational time and the memory cost will increase a lot. This makes it further difficult to be included in our current BOO framework because we already have over 10,000 candidate beams, 1,000 candidate beams. And if we need to consider 10 worst cases, and then we will have 10,000 different cases. That is really making the problem too large to solve. So the aim here is we want to develop an integrated framework that can include more computationally efficient, robust penalty, still use a single step to give us the beam and the fluence map in which is robust and have a good dosimetry. So that's the goal of this part of work. Let's look at how the problem can be formulated and be solved. The first term, the first function is just the dose fidelity term we already mentioned in previous work. It's used to encourage less physical dose deviation from all candidate beams. And the second term, if we ignore the H sub B coefficient, it's just the L2 1/2 norm group sparsity before we mentioned used to select a few beams out of all candidate beams. But in this term, there's no robustness is considered. So we add this HB item. It's a heterogeneity index of beam B. It quantifies the lateral tissue heterogeneity observed along this beam. And why it's important and why we want to include this, because in clinic, higher tissue heterogeneity is usually associated with higher setup uncertainty. So if we select beam passing more less homogeneous tissue, then the plan tends to be less robust. Therefore, adding this weighting to the group sparsity, we call it heterogeneity weighted group sparsity. It will encourage as an algorithm to select beams with passing more homogeneous tissue. therefore making it more robust to set up uncertainties. And the third part is a sensitivity regularization. And this function has this part has two aims. First, because only setup uncertainty is handled in the second term. So we use this term to promote beam robustness to range uncertainties. And we also want to use it to make entire fluence map more robust to both range and the setup errors. Here, SK or SU or SV, they are the spot sensitivity vectors along beam direction and the lateral direction. We derive this by calculating those gradient between the adjacent spots. And so for one spot, if the sensitivity value of that spot is high, that means that the spot is more easy to these uncertainties, and we are penalizing these spots harder. So one difference we can see is we don't have any worst case method here. We don't assume what's the worst case and what the worst case can happen. And what we are doing is we try to see how the spot behavior is and to penalize. So here we formulate this BO framework for robust optimization. We evaluate with 2 head neck patient and a 2 skull-based chordoma patient with the following setup and a range uncertainty for robust analysis. Okay, let's look at some results here. So first we want to see how robust our selected beam is. So here shows the CTV DVH band for range uncertainty on the left and the setup uncertainty on the right. This shows the same CTV structure, but on different beam arrangement. You can see, so let's take a look at the most back one that manually select beams. You can see that the band is slightly wider under this range uncertainty, means the plan is slightly less robust, or the beam is less robust. And on setup error, it's like narrower band. I also label the worst D95% using the reference line on the XY plane. And this means the coverage of the CTV under worst cases. And usually the more this reference line is pushed to the right end, then the CTV is better covered. I'm going to skip this middle 2 beam arrangement and directly go to our method. We can see for beam, it has our method, which is to the most front one. It has a very much narrower band compared with this manually selected beam under range uncertainty, and the bandwidth under setup uncertainty is similar. For coverage wise, setup range coverage much better and the setup coverage comparable. And here is another beam robustness result for the head neck patient. We also see much narrower band using our method for this patient compared with manually selected beams. Before is the beam robust, how robust the beam is. And now let's look at how robust the final plan is using our method versus the conventional method. While the conventional method is the plan with manually select beam and the worst case FMO, we see our plan for this patient has a narrow band for this CTV and the similar coverage showing here in the reference line. And the setup uncertainty wise, our plan is slightly worse, but still improved from conventional non-robust plans. Here's the similar results for the head neck patient. So far we see that our method is able to generate robust beam and a robust plan that comparable to the conventional method. We also find we are able to spare the OARs much better. Here shows the DVH comparison when there's no errors between our method in solid and the conventional method in dotted. We see for the OARs, our method is much lower, like to the right optical nerve and the chiasm for this case. For the head neck case, we still see the similar observation, lower dose like for the middle ear, but just to the second case, the dose to the right submandibular gland is slightly higher. Here it shows the average reduction of the OAR mean and the maximum dose. Computation-wise, depending on the target size, the process takes about 6 to 45 minutes to complete. This is longer compared with our last study, because in this study, the target size we choose is much larger. In conclusion here, we developed an integrated, robust optimization method. Yes, to our knowledge, it's the first work to solve robust BOO and a robust FMO in a unified framework, generate plans with superior dosimetry and a good robustness. It shows a good improvement in the planning efficiency compared with the trial and error manual selection process. I'm running out of time here, but I just want to say that this framework also gives us this very flexible platform to try to understand and solve more problems. Like I use this to formulate a new framework to select different beam arrangement in different fractions, to include biological effectiveness into BOO, and also use, instead of just for beam orientation optimization, I use it for proton arc therapy, try to optimize the energy layer trajectory during gantry rotation, and we can still see the growth sparsity penalty in the function. Thank you. Here's the reference that if you are interested, you can find the works in these papers. And I want to thank a radiation oncology team from UCLA, Penn, and Dr. Kishan lab from UCLA and UT Southwestern Radiation Oncology lab. Thank you so much. I am happy to answer any questions.